All right, what we were looking at yesterday was called the inverse of a function. And it's a very special type of transformation. It's where you swap x and y for every point. A few things that you need to remember about that is that, first of all, the two things are reflections of each other across the line y equals x. That's what it looks like visually. Everything that's true about x on one of them is true about y on the other. So whatever the range of one of them is, that has the same properties as the domain of the other. If the x-intercepts are 1, 5, and 12 on one of them, then the y-intercepts will be 1, 5, and 12 on the other. Pretty straightforward there. If you want to determine the equation of an inverse of a function, you've got to rewrite the function with y instead of f of x, and then switch x and y and rearrange for y. Okay? The inverse of a function may be a function or it may not be a function. You can use the vertical line test to determine if the inverse is a function. How many of you have encountered in your textbook the phrase horizontal line test? It's in there. So if I gave you this function, I'll just make one up. And I said to you, so this is a function. This is f of x. And I said to you, is the inverse a function? What your textbook does is it uses what's called the horizontal line test. You would use the vertical line test on the inverse to determine if the inverse is a function. Or you could use the horizontal line test on the original to determine if the inverse is a function. And the reasoning is that since this graph crosses a horizontal line in more than one place, the inverse will cross a vertical line in more than one place. Does that make sense? So don't be confused by the horizontal line test. It's just saying you don't necessarily need to graph it. What I've told you is if the function goes up and down, the inverse will not be a function, because the inverse will go back and forth. And lastly, you need to know how to restrict the domain of a function so that the inverse is a function. So if you take a look at that parabola, the equation of the blue parabola is at the top of the page, f of x or y equals x plus 3 quantity squared minus 7. And really from Math 20-1, you should be able to graph that without using a graphing calculator. Again, the reason why the inverse of that blue function, which is the red one, the reason why the inverse of the blue function will not be a function is because the blue function goes up and down, so the inverse will go back and forth. Instead of going up and down, it will go right and left. So to restrict the domain, we could just say, since the center part of this parabola was at h, which is negative 3, you could say x is less than or equal to negative 3, which leaves only this half of the parabola, which would mean since there's a left half, the inverse will have a bottom half. Left is negative, bottom is negative. Or you could say, I'm going to go with x is greater than or equal to negative 3, in which case there's only a right half, which means the inverse will only have a top half. Let's take a look now at textbook questions. Any questions you would like me to go over from the textbook? All right. Any questions anybody would like me to go over from the multiple choice numerical response section? Skylar. Number 5. So we're asked to determine the inverse of this function. This is a typical kind of numerical response question. Remember, Skylar, to determine the inverse of a function, you swap x and y. But before I swap x and y, it's a good idea for me to write this using y, right? I mean, I can leave it as f of x, but then if I went right from f of x and I put x there, because I'm swapping x and y, it might confuse you and other people. So this is the first thing I'm doing And again, this is still the original. That's still the original function. The inverse would be x equals 2y minus 5. And all we have to do now is rearrange it for y. The fact that you're told this, everybody, means that whatever the inverse is, it is a function. Which means, I guess it means in terms of equations, there's no plus or minus. There's other ways you can get things that are not functions other than seeing a plus or minus, but we don't need to worry about them right now. The bottom line, by the way, is if I rearrange this for y, I'm going to get 2y equals x minus 5. So I'm going to divide both sides by 2 and get y equals 1/2 x minus 5/2, which is a linear function. And since it's linear, it's a function, a straight line with a slope of 1/2 and a y-intercept of -5/2 will pass the vertical line test. Right? So are you okay with this?
Yeah.
A is 1, B is 2, C is 5, D is 2.
Yeah.
Any other questions? All right, we're going to move on today. Your unit exam is next Friday. This is on page 31, I believe, of your unit handout. Is that right, page 31? No. Is it? 32. Page 32 of your unit handout. Your unit exam is next Friday, so I believe we have 3 more lessons to cover, one today, one tomorrow, one on Tuesday of next week, and then Wednesday and Thursday are review days. I always try to have 2 days for review before an exam. So we're looking today, we're jumping now into chapter 2. And we're going to be looking at knowing what the graph of f of x equals root x looks like. We're going to be graphing any transformations of root x. And we're going to be identifying domain and range of radical functions that are transformations of root x. So I'm not quite sure why the textbook writers chose to have a special section for root x. Okay? But let me explain to you the rationale. If you know the properties of some base functions, then you can determine the properties of any transformation of them. For example, in grade 11, you learn about quadratic functions. Specifically, you know what y equals x squared looks like. It's a parabola with that point, which is called the vertex at the origin, and it opens upward like this. It goes over 1 and up 1, over 2 and up 4, over 3 and up 9. You know what that looks like. So even though in grade 11, you never really used a b, you didn't. There was no b when we talked about quadratic functions. And the a you were taught about, you were just told, well, it makes things skinnier or wider. Does that have vague recollection for you guys? That if a was 2, it just got skinnier. Well, now we talk about stretches. But there's a b here as well. So if I say to you at this level, graph or tell me everything you know about that, where the function is squaring, then you know since b times x minus h is being squared, the function is the input squared. You can tell me that this function will be this function after being reflected vertically across the x-axis and being stretched vertically by a factor of 1/2, and also being stretched horizontally by a factor of 1/3, and also being shifted to the left 4 units, because you have to factor that 3 out. So after the reflection and stretch and stretch and shifting 4 to the left, it shifted 7 down. You can tell me about the properties of that graph because you know the properties of the starting function. And the reason why I said to you, I'm not sure why the author of the textbook chose to have a section just for root x. The reason I said that is, I mean, you should be able to apply this to anything, right? If you wanted to apply this to x cubed, you've never been taught what x cubed looks like. But it would be a pretty trivial matter for you to put it into your graphing calculator and see that x cubed looks something like this. Okay, and it doesn't matter if you knew that already, although maybe you did. The point is, if f of x is x cubed, and I'm not going to do this for every one of these I'll reveal, you should be able to tell me what this will look like. You should be able to tell me what that function looks like. And you would arrive at your description by taking everything that you know about this shape, reflecting it vertically, stretching it vertically by a factor of 2, stretching it horizontally by a half, shifting the result 3 to the right, and pi units down. You guys with me on this? And again, just to make sure, the f is that, because it says f of x is x cubed. Okay. All right, so there's all these functions. For example, x to the power of n. It turns out that whether x is to the 2 or to the 3 or to the 4, if you knew what it looked like, you could call that a base function, a starting function, and you could apply all those changes to it. 2 to the x, which is called an exponential function, and we have not learned about that yet. We are going to learn specifically about that function, is a base function. The absolute value of x you learned about last year. It's that v, right? So really, I ought to be able to give you any absolute value function in the universe, and you can make it match this and tell me what it looks like. Sine x is one we'll look at. Cos x, log base 2 of x, 1 over x. These are all functions that we are going to be studying in detail. However, this one, there's not really too much special about it. But we're going to be doing that today. Okay? And then the rest of this chapter is dealing with square roots in general. And that's where it will get a little interesting. So to begin with, we call these functions radical functions. Last year in Math 20, you studied radical expressions. Root 2x is a radical expression. You studied radical equations. Root 2x plus 5 equals x minus 3. That's a radical equation. What a radical function is a function that contains square roots. So these are all radical functions. They contain a y variable, or f of x, and they also contain an x variable. I'm limiting myself to y and x here. They don't have to be. They could be p and n. They could be any letters you want. But one of the variables, the independent variable, which in this case is x, is under the square root sign. And when you take a look at these three radical functions, I hope you would agree that this is simplest. Like there's a level of complexity to the other ones. And that's why we call it the base function. So what we are going to do is sketch this graph. Now we won't need rulers because these graphs are not straight. They don't have straight line segments. One thing I want to point out to you is that when you see this radical sign, and this might have been lost on you in grade 10. It doesn't mean plus or minus. It means the principal or positive square root. There's only one time where you write plus and minus, if it's not already written, and it's when you take the square root. So if I go from x squared equals 9 to x, I have to go x equals plus or minus root 9. But if it's not there, it's not there. So let's choose for an x-coordinate 1, and I hope you see why I'm choosing the x-coordinates I am. The square root of 1 is 1. The principal square root of 1 is 1. If I take a look at x equals 4, the principal square root of 4 is 2. You can see that I have planned this out by picking x-coordinates that make our lives a little bit easier, and I've given you a grid that's all ready to use because I know what this shape is going to look like. The square root of 9 is 3, the principal square root of 16 is 4, and of 25 is 5. So now it becomes a matter of plotting those points, that's all. One point, and I realized this just today as I was finishing this lesson on the notebook program, I didn't put 0 for an x-coordinate. I could put 0, couldn't I? And the square root of 0 is 0. Can I put -1? I can't take the square root of a negative. So we can plot 0, 0, we can plot 1, 1, we can plot 4, 2, all the way down the line. And what we're getting, what we are getting is really half of a parabola. I don't know if you remember, but a few minutes ago I said, when you look at x squared, there's a vertex, and we go over 1 and up 1, right? We go over 2 and up 4, and we go over 3 and up 9. Well, here, we're doing the opposite. We're going over 1 and up 1, over 4 and up 2, over 9 and up 3. It's a parabola that's laying on its side, but it has no bottom part. And please don't write this, but if this function were plus or minus root x, don't write that, then what we would get would be this, and it would be the inverse of x squared. So this is only half of the inverse of x squared. And you do your best to draw this. I'm not worried about your artistic skills. You know, some of us, particularly if you've had a lot of coffee, you might be shaking as you draw it. But it's this kind of smooth curve. You'll notice that I kind of copped out there. I didn't draw it myself. I pasted in what it looks like because it's hard to draw. Here's some advice in case you are expected to draw something on an exam, and you could be. When it's a curve, I liken drawing curves through points to driving. If you're driving down the highway and you're looking 3 feet in front of your bumper, I don't want to be around you. You should be looking ahead at where you're going, not where you're going to be in a split second. So when I start to draw this, if I'm only looking at the next point, people tend to kind of do kind of a boxy method. It's not smooth. But instead, if you start drawing here, and I'm looking at all these points, I'm looking ahead to where I'm going, it's not bad. I got there's a dip in the floor right here, I think. I'm just kidding. Got a little wavy there. There we go. I was walking and drawing at the same time. So if you are, and you could be expected to draw something, that's just a piece of advice. It doesn't have to be perfect, though, for the case of our lesson. So this is what it looks like. What are we asked for? We are asked as well, I believe, to state the domain and range. Before we do, your textbook calls this a vertex. It is not a vertex. This is a cusp. And I've never seen the word vertex used on a diploma exam. I have seen the word cusp used. I'm not saying it couldn't be called the vertex. It's just that's not the right word for it. It's called a cusp. A cusp on a graph is any point on a graph that kind of either ends, or if I had a graph, and those of you taking calculus will see lots of these, you have a graph which maybe looks like this. That's a cusp. It's a pointy part of the graph. Okay? In fact, when you look at an absolute value function, that is what we can call it. Okay? Although in grade 11 you call it a vertex. Just a point of interest, now we're asked for the domain and range. You can see that this graph continues to the right forever, which means the domain is x is greater than or equal to 0, and the range is y is greater than or equal to 0. And the cusp is at 0, 0. So from now on, you should just know that that's what y equals root x looks like. The reason why I don't think it's that big of a deal, to be fair, is you could always just put it in your calculator and remind yourself what it looks like. All right. All radical functions can be graphed by transforming that most basic radical function that we just graphed. So if, and I'm going to show this to you, if this is our template, and it is, and f of x is root x, and it is, then I'll remind you, and I know that you probably go, oh, yeah, I get it, but I like to do it every time. If f of x is root x, then f of 3 is root 3. F of diamonds is root diamond, which means that f of b bracket x minus h, this piece right here, is the square root of b bracket x minus h. Right? F of b times x minus h means you're going to take b times x minus h and replace the x in the function with it, and the function is the square root, so we get y equals a times, while we replace b times x minus h with the x that was under the square root, and then we add k. So that's how this thing is arrived at. I mean, again, if I told you that f of x was, oh, let's just go nuts. Log base 2 of x over tangent of x. Okay? That's a function. Who knows what it looks like? I don't. We could figure it out, but it's not important. And I said we're going to transform that using this. Then this new function would be y equals a multiplied by, I have a feeling I'm going to need a big set of brackets here, the original function, but everywhere there was an x in the original function, I'm going to put b times x minus h. And then I'm going to add k. So it doesn't matter what the function is. B times x minus h is what x turns into. All right. It's not on your formula sheet, but as I said, if you know this and this is on your formula sheet, you ought to be able to get that. Let's take a look at these examples. We are asked to sketch this radical function. And I don't know that I put room or left a, b, h, and k there, but write down a equals b equals h equals k equals. Take a minute, look at the function, and compare it to the original function, which is root x, which is up here as well, and identify the values of a, b, h, and k. I hope we're okay with those numbers. That a is 3, b is -1, h is +5, and k is -1. I don't have to, but if I want to, I can rewrite this as y equals 3 root -1 x minus 5, and then -1 to see the values of a, b, h, and k. But does anybody have any questions about getting those numbers? Are we okay there? Okay, so, you know, this question is not asking you to verbalize or write down what the changes are, but I will say them anyway. In fact, I'm going to write them right here. We've got a vertical stretch by a factor of 3. We have a horizontal reflection. We have a shift of 5 units to the right, and we have a shift of 1 unit down. You don't have to write those down. I'm just writing them down because I feel as though I should, but I think everybody should be able to look at those parameters and tell me that this is what happens. Would you agree? if you don't know that by now, you got to figure it out very soon because we're running out of time then. So I am going to regraph this by taking some key points. I'm going to take the cusp, which is at the origin, and I'm going to stretch it vertically by a factor of 3, but that will not move it. And then I'm going to reflect it horizontally, but that will not move it. And what we discover after we move it 5 to the right and 1 down is that the cusp is always at h, comma, k. Do you remember last year with parabolas that the vertex was always at p, comma, q? The reason the vertex is always at p, comma, q for a parabola is that reflections and stretches don't move that vertex that's at the origin. It's only the p and q that move it. P, of course, this year has become h, and q has become k. All right, let's go to the next key point, which is at 1, comma 1. And I really like doing this rather than the mapping. I can show you the mapping, but again, I think it's more fraught with error, with chances for error. So I'm going to take this point and I'm going to stretch it vertically by a factor of 3. It was 1 away from the x-axis, now it is 3 times further away. And then I have to reflect it horizontally, which puts it here. And then I need to shift it 5 to the right, 1, 2, 3, 4, 5, and 1 down. You will notice, well, you'll notice something when I point it out to you. If you look up here, at the original y equals root x, the first key point, which was the cusp, you went over 1 and up 1 to get to that next key point, right? This key point now, from the cusp, you go over 1 to the left, and you go up 3. So why are we going to the left? Well, because b was negative, it flipped it. Why are we going up 3 instead of just up 1? Because the vertical stretch factor was 3. Right? If I would have stretched it vertically by a factor of 3 and actually shown you the graph, it would look like that. When I reflect it and then shift it over, we're going to be down here. If you feel the need to draw this, okay, and then draw this, and then shift it 5 to the right and 1 down, you can. You can do this in stages. Do you understand what I'm saying to you here? I think most people are probably fine just doing what we're doing because I think, quite frankly, the more stuff you do here, the more confusing it gets. If you were maybe doing a written response question, you might do it in stages. Let's move on. I have a feeling I covered up a key point here by plotting that new point, didn't I? There was a key point that was here already. So the key point that's at 4, comma 2 is stretched vertically by a factor of 3. So now it is 6 away. It is reflected across the y-axis, and then it is shifted 1, 2, 3, 4, 5 to the right and 1 down. I think we have enough room that we could do that last key point as well. Stretched vertically by a factor of 3 will take it to 9. I better just count my squares here and make sure this is correct. So that takes it to 9. Now I'm going to reflect it, and it's 9 to the right, which means it's going to be 9 to the left. 5, 6, 7, 8, 9. And now I'm going to shift it 1, 2, 3, 4, 5 to the right, and 1 down. So if I draw a gentle curve from that cusp, which is at the bottom right, through these points, I get a picture. See how I do? I get a picture. That's not bad. Of the graph. I really have a feeling, you guys, that if we were interested on an exam, we being our school and the Alberta government, were interested on an exam of your ability to graph these things, the function would probably be a series of line segments to begin with, and not a square root function, not something with a curve. What were we also asked for the domain and range? Okay. So y is greater than or equal to negative 1, and x is less than or equal to 5. And by the way, I know that, and I didn't even look at the graph. I know that because, now look up here again, root x starts at the origin and does this, right? And it goes up forever. So y is greater than or equal to 0. By me shifting it down, it's still going to be y is greater than or equal to some number, but it will be greater than or equal to k, because k is where that lowest point is now. When I look at root x, which is the blue graph, x is greater than or equal to 0. Why did I put less than or equal to 5? Well, I put less than or equal to because that negative b reflected things horizontally. So instead of taking off this way, it takes off this way. But that h value of 5 still puts that cusp over at an x coordinate of 5. If you were to do the mapping, and I feel as though I probably should, because maybe on a diploma exam you might be told to explain the mapping. You should understand it. The mapping here is that x comma y becomes, now I'm working this out. It's not in my head. I'm looking up top and I'm seeing that there's a vertical stretch by a factor of 3, which means y gets tripled. And while I'm looking at the y's, it also shifts down 1. So this is the mapping for y. The mapping for x would be negative x plus 5. I have to multiply x by negative 1 to reflect it, and then I need to add 5. So you certainly do not need to write down what is about to come. We could have graphed this resulting thing by taking 9 comma 3 and putting the 9, because it's x, wherever there's an x. And taking the 3, and because it's y, putting it wherever there's a 3. Now what do we get? We get that 9 comma 3, which was this key point, becomes negative 4 comma 8. Would you agree that that's what these numbers become? Negative 4 comma 9 minus 1 is 8. Well, where's negative 4, 8? Negative 4, 5, negative 4, 1, 2, 3, 4, 5, 6, 7, 8. Like you could have done that with every point. I'm not a big fan of that. I don't know why. I think that's just a lot of room for error. Are you getting my drift here? Okay, let's take a look at the next one. I would like everybody to take a moment and identify the values of A, B, H, and K. Liz, are you here for the rest of the class?